So far we've dealt with base 10 and other bases. There's the last thing is called the natural base, and it's e. And e is kind of like pi. It's called an irrational number. In other words, I can't write it as a terminating decimal or a fraction, right? But pi does have an approximation. And where pi is used is in the compound, or when e is used is in the compound interest formula. That when we're trying to compound interest continuously, we use e to do that. And so e it's used quite a bit in the banking world, business world, when we were talking about interest. And if you're putting money in the bank in a savings account, you want it to be compounded continuously, which means that they have to use a specific formula called PERT that involves E in it. So all it is it's another number. Okay? The actual approximate value is 2.7182818, which they show right here in the middle of the screen. And like I said, it's similar to pi. Right? So I can write it in exponential. Here it looks like all of our exponential functions. Okay? When it's graphed here, f of x equals e to the power of x. When I graph that, I just have the domain is all real numbers and the range is y is greater than 0. Right? Well, the inverse of that then is going to be what's called the natural logarithm. And this is also on your calculator. This, on the natural logarithm on your calculator, it's the key right below the log key. They use ln instead of nl, though. I'm not sure why, but I guess it's probably the guy who created it said, hey, those are logarithms al naturel instead of natural logarithms. So that's my take on it anyway. All right. So, like all exponential functions, once again, the domain is all real numbers. The range is y is greater than 0. So if we did the inverse of it, then the domain would be x is greater than 0, and the range would be all real numbers. So I want you, first of all, we're just going to look at some graphs of them. And so, we're going to make rough sketches of these. We're not going to do exact graphs of them. But let's just see what we have when we have a transformation of one. So go ahead and put that in your y equals and graph it. And E is second natural log, second ln key. Oops. Is that plus 1? Okay. All right. So the only difference is here, comparing it to our other exponential, is in this case we said that plus 1, which means that our range has changed. Instead of the range being y is greater than 0, the range to be y is greater than 1. Just a little shift. But all I'm going to expect from you on these is just that you can graph them. Okay, that if I give you a graph on a paper, say graph that, you can plot some points, go find a few points, plot them, and draw the graph. Okay. So let's go back and let's just look at the e to the power of x. So graph just e to the power of x. Right. When we look at this graph, it looks like any other exponential function. Okay. All right, and then graph in y2 the natural log of x. So the ln key of x. And I'm also going to put in y equals x here so we can see the that line. Right. So we can see that the e to the power of x, natural log of x, those are inverses because they are reflections across the line y equals x. So when I put them together, and we can also see that with the natural log of x, the domain, x is greater than 0, range is all real numbers. So when we put those together, those are inverses. So they're going to act on each other the same way that they do with logarithms. So here, this is just an exercise that was very similar to the warm-up, where we were just working with, hey, if I have a base, logarithm, if they're the same, they undo each other. So the natural log of e to the power of 0.15t, well, natural log, so ln is the same as we said, this was log base e of e to the 0.15t power. Right? So if I said natural log, it basically means a log with a base e. Well, since these two things are the same, they undo each other, and our answer is 0.15t. Okay. So letter B, remember, first thing, before we can simplify this, we need to take that 3 and move it to the exponent. So since this is, our base is e, natural log has a base of e, so the answer to this is x plus 1 to the third. And don't multiply that out. That would just be more work than we want right now. Okay. And letter C, natural log of e to the 2x plus the natural log of e to the x. Well, the natural log of e is equal to 1. Because those are inverses of each other. Right? Just like the log of 10 is 1. Or the log base 3 of 3 would be 1. Okay? Same thing. So for letter C, this is just 2x plus x, which is 3x. Right? Because these two things undo each other, these two things undo each other, so we just get 2x and x, or 3x. All right, so you find these three answers. Okay. All right, using E. I was telling you earlier that there's this formula called PERT, for compounding interest continuously. And here's the formula. It says A equals P times E raised to the power of RT. Now, in the first lesson of this chapter, we did exponential growth and decay. Right? There's also a compound interest formula that's similar to them, which says that A equals P times 1 plus R over N to the power of NT. Right? This is the compound interest formula, where it looks the same as the exponential growth. It's just that if I do them more than once a year, the value of N takes that into consideration. So you get a bank statement. If you have a savings account, you probably get a bank statement every 3 months, so quarterly. So what they do is quarterly they calculate interest on how much money you have in the bank, in your savings account. So they would put a 4 in for n in those cases to be able to solve that. So it's the exponential growth function. It's just that if they do it more than once a year, then n takes into account how many times a year they calculate it. Right? Well, with PERT, they compound the interest continuously then, which is better because it gives you more money. And that's what you always want them to do. Right? So we're going to use this formula then to solve a couple of problems. It says, what is the total amount of an investment of $500? What is the total amount for an investment of $500 invested at 5.25% interest for 40 years and compounded continuously? Right? So if you can leave money in the bank for 40 years, you're awesome. Okay? Right? That should be a goal. You put some money in the bank now and let it stay there forever. Unfortunately, nowadays, you're never going to see 5.25% interest. Okay, unless they're charging it to you. They're certainly not going to give you money at that rate. But anyways, right? So because it says they are compounding it continuously, we're using this formula. A equals PE to the power of RT. And so we do this just like we did the compound or the interest growth and decay. All right, P is still our initial amount, 500. We have E, our interest rate. We're going to change that to a decimal, so 0.0525. And then we're going to, our time in this case is 40 years. Then we just type that in our calculator. $500. Then we go to second ln, 0.0525 times 40. So that $500 in 40 years would be $4,083.08. All right, so I would write a sentence to say that. All right. So what if we have an investment of $4,500 at 5% interest, compounded continuously for just 6 years? You go ahead and find that one. We have one more example to look at then. All right. Deals with half-life. Right? How many of you have dealt with half-life in your science classes? Okay, all right, so it shouldn't be too big of a deal then. The half-life of a substance is the time it takes for half the substance to break down or to convert to another substance during the process of decay. Natural decay is modeled by this function. N of t equals n sub 0, which is our initial amount, times e raised to the power of negative kt. And it says k is the decay constant and t is our time. So it says plutonium-239 has a half-life of 24,110 years. How long does it take for 1 gram sample of plutonium-239 to decay to 1/10 of a gram. All right, so the first thing we need to do is we need to find K. We need to find the decay constant because we need that value to be able to complete this problem. Because they give us our starting amount, which was 1 gram. They tell us our ending amount is 0.1 grams. And they tell us that the half-life is 24,110 years. So we need to use that information, first of all, to find K. And then we can determine, then we can find out how long it's going to take. So we plug in what we know. We know that our finished amount is 1/10 of a gram. Our starting amount is 1 gram. And e to the negative k times 24,110. All right, so we're using what we know to be able to get the value of K so we can figure out how long it's going to take to get there. Because we can't have two missing variables, okay? Two unknowns. All right, so let's rewrite it. So we have 0.1 e to the negative 24,110 K. All right. So here we have an exponential equation. And what did we say to do with the exponential equations? We said, first of all, we're going to look to see, can I make the bases the same? All right. And I don't think I can change e and 0.1 and make them the same. All right. So what do I do after that then? If I can't do that, what do I do? We said we take the log of both sides, right? Because we're going to change it from exponential to logarithm. But in this case, because the e is involved, we want to use the natural logarithm. So the natural log of 0.1 equals the natural log of e to the negative 24,110 K. And the nice thing here is that what do natural log and e do to each other? Okay, they cancel each other out because they're inverses. So the natural log of 0.1 is equal to negative 24,110 K. And divide by negative 24,110. So K is approximately, so I'll take my calculator, natural log of 0.1, close the parenthesis, divide by negative 24,110. Right, we get that number there. Okay, what is that number? So we have to move the decimal place 1, 2, 3, 4, 5. So we have 4 zeros. So it's approximately 1,955. There's our decay constant. All right, I moved the decimal place from here 5 places to the left, which put me with 4 zeros. Okay. So now that we know K, we can go in and find that time then. So everything else is still the same, except we are now not using our time because we're trying to find the time. So everything we do is going to be the same except for we're replacing K with the number that we calculated, and then we're going to find the time this came. So natural log of 0.1 equals negative point. So we divide by that number. So natural log of 0.1, and I'm going to divide that by my, oops. Let's try that again. And to get the answer, the previous one, you just hit second, and negative key puts it up there. All right. So we get, I just did something wrong. Let's see what I did wrong. All right, so I goofed up. All right, it's not the first time, won't be the last time, and probably nobody saw this. Okay, all right, but does anybody know where I made the mistake? Can anybody guess where I made my mistake? And it's not in the blue; it's in the black. Okay, I did that here, but I mean, I didn't know that here in the black stuff. Okay, all right. So here's the mistake I made. All right, our time 24,110 represented what? What does that represent? Represents the half-life, right? Okay, and I said that it represented getting it to 1/10, not to 0.5. So, mistake I made, my apologies to you all, is that this should have been 0.5, not 0.1. So we got to change all these to 0.5, which will change our value of k. Right. Good learning. Right? You're not learning if you don't make mistakes, or you're not trying if you don't make mistakes once in a while. All right, so change all these 0.1s to 0.5s. Right. Which means I've got to get rid of all this and start over here now. All right. So natural log 0.5 divided by 24,110. Oops, and it should be negative. All right. So it's 287 instead of 955 is our number. So 0.1 now All right, that makes more sense. So let me ask you this. When we're done, okay, is my value of time, the number I get for time, should it be more than the time for half-life or less than the time to get to half-life? Should it take me longer to get to 1/10 or shorter to get to 1/10 than it does to get to 0.5? So is more decaying or less decaying? Okay, more is decaying, so it should take us a little bit longer to get to 1/10 versus 5/10. All right, so we're going to have natural log of 0.1 equals negative 0.0000287 t. Sorry about that. So I'll divide by that. I knew I was going to at least make one mistake today. There we go. 80,229 years. So it's going to take almost 4 times as long to get to 1/10 compared to getting to half. All right, and I'm not sure who's going to be around to verify that that's true or not. Okay, that's my biggest thing about them using half-lives and predicting things is like, yeah, nobody's going to be around to know the difference anyway, and so to know whether you're actually right or not. So in these problems, you got to make sure you use the half-life to start with, and then go from there. Okay? All right. Here's your assignment.